Sure. There's actually quite many people reading.
Oh, really?
Yeah. Yeah. Okay, it's 2 o'clock. It's 2 o'clock. Let's get it started. It's a great pleasure to have Andrea, Porro, right, and
Perfect.
from Darmstadt to give today's presentations. So first of all, let's give some information about him. He's really young. He got his PhD last year from Sackler in France, and I think he just started his postdoc in Germany at Darmstadt, working up in front too. And his advisor during the PhD, two advisors. One's Thomas Gavier, right?
Yeah.
The other one's Victoria's Samant. And so today he's going to talk about ab initio distribution of monopolarities. And please take it away.
Okay, thanks a lot, Shilin. Thank you for having me here. If it's not a problem, I will not use the microphone, but I guess I can speak sufficiently loud. This work I'm going to present is since I've just relatively finished my PhD, has been realized during my PhD collaboration with my PhD advisor, but also with which are Thomas Duguay and Vittorio Soma, but also with Michael Frosini, who is also in CA. And yeah. Okay, I'm sorry. Okay. Is it better? Okay. So so this work, which I'm going to show, was recently posted on the archive in 2 papers, which are actually the first of a series of 4, because someone like monographies. And yeah, so if you want more details on that, you can find it on the web right now, then more are coming soon. But I think there are 2 keywords which I need to introduce in my work, which are in my title. So the first keyword is ab initio, and this will represent the first part of my introduction. So trying to describe a bit which is nowadays the global philosophy concerning ab initio nuclear theory, which methods have been used, and what are the frontiers that we are trying to cope with these days. And the second keyword is giant resonances. So I will address the physics case, which I'm trying to investigating, of course, also mentioning the methods which are already being used in this domain. Then I will introduce the method which I have used during my PhD work, which is PGCM, which stands for Projective Generator Coordinate Method, and also trying to touch upon the problem of uncertainty quantifications in this field, before showing some selected application, especially concerning the physics of deformation and resonances, the observation of multi-phanon states, and also possible links between finite nuclei constraints and astrophysical observation, before, of course, going through some conclusions and perspectives. So let's get started. In this picture, which I guess no one of you have ever seen before, we can appreciate the several energy scales at play in nuclear physics. And one may try to, sorry, I don't know. one may try to start describing the complexity of a nuclear system, starting from the very bottom of the theory, which is quantum chromodynamics. And this would be naturally the more elementary description of the problem, and is basically what is done, for instance, in lattice QCD theories. Otherwise, in a more lower energy perspective, at ab initio, we start from so-called ab initio effective field theories, which have several inclinations nowadays, such as chiral, pionless, or cluster effective field theories, and in which one observes the emergence of effective degrees of freedoms at lower energies, and specifically in chiral effective field theory, which is the method I started from. One starts from structureless protons and neutrons, and the interaction is mediated by pions and contact terms, such as when one comes to the many-body Schrödinger equations, which we are trying to solve, we notice that in the nuclear many-body problem, we have actually two unknowns. The first one is represented by the Hamiltonian, which should input our calculations, whereas the second one is, of course, the many-body solution itself of the problem. In both cases, one aims at expanding in a systematic fashion both quantities. And for instance, concerning the Hamiltonian, this is related to so-called chiral expansions, in which there's a given number of contact terms I was mentioning before, called low energy constants, which are fitted on on two-body scattering data, but in principle, of course, includes up to A-body forces. And otherwise, as far as the many-body part is concerned, there are many methods in which so-called expansion operator method. One starts from a reference state, and via the action of a wave operator, get a more and more precise solution for the many-body problem. But I will detail a bit the methods which have been used in the next slides. So that overall, we see that the global philosophy of nuclear theory is that the approximate solution that we get should be systematically improvable and approach the exact solution in a well-defined limit. Since at any point of our calculation, we are introducing actually some sort of uncertainty, we also should be able to quantify those in the most precise fashion, even if it's a very difficult task. I would like just to highlight some of the methods which have been used in the last 20 years or so in ab initio nuclear theory. And at the beginning, so starting from 20 years ago, only so-called virtually exact methods were used, and they are used nowadays as well with better technology. But these methods can be used only for relatively light systems because the cost of the problem increases in a factorial way with respect to the number of nucleons in the system. Methods are Monte Carlo method or no-Korshell model, and they provide the explicit two-body solution. Otherwise, I was mentioning before, we have a second category of methods called expansion methods, in which one has a much milder polynomial scaling, which allows to explore also heavier systems, in which this ground state is expanded in series via the action of a wave operator, and there exists perturbative or non-perturbative methods. So starting from 2005, these methods were only applied to symmetry conserving single reference state, and such as just to mention a few, many-body perturbation theory, couple cluster method, self-constituent function, and in medium similarity normalization group. But then one very soon noticed that those break down for open shell systems due to valence shells degeneracies when employing a symmetry conserving reference state as a starting point, such that starting from 2011, symmetries, underlying symmetries of the Hamiltonian were broken by the reference state one is starting from. At the beginning, only the U1 symmetry was broken, so the symmetry which is related to the good particle number in the systems, giving rise to the Bogoliubov generalization of the previously mentioned method. And even more recently, in order to tackle also doubly open shell systems, the rotational systems, the rotational symmetry has started to be broken for the reference state, originating the formed versions of all these methods. So, and here we have all possible combination of the formation and the U1 symmetry breaking, even if not all of these have been implemented up to date. However, one should specify that when starting from symmetry breaking reference state, the symmetries should eventually be restored by the final, the whole many-body machinery. And in order to have wave functions which carry the good quantum numbers and preserve the symmetry of the original Hamiltonian. And eventually, all in all, my also bottom line here is that all of the methods which I've been mentioning here has been used up to now, essentially, not exclusively, but for ground state calculations, so to address ground state properties of finite nuclei. This brings me to the next slide. So what are nowadays the current frontiers in ab initio nuclear theory? First, of course, we have the quest for more and more accurate calculation, which originates in the production of more and more accurate Hamiltonian and many-body method, but also the sound quantification of uncertainties, may they be of systematic or statistical nature. Then we have a whole world apart, which is the reaction theory, and the one towards heavy mass systems. Here, a picture from a relatively recent paper with calculations for leg 208. And I was mentioning before also the calculation for open shell systems, and eventually the access to excited states, so the spectroscopy frontier, which can be very solidly divided into single particle and collective excitations. In my work, I have focused on this last aspect, so the access of collective excitations or spectroscopy, but for open shell systems, so without any limitation in terms of symmetry, and possibly trying to do our best for the quantification of uncertainty. But let's now try to describe a bit the physics of these giant resonances that I'm trying to study. In this sketch, I am showing the cross-section of an imaginary scattering experiment. And I think that here we can quite well appreciate the very dual nature of nuclei, which single particle feature coexist with a very collective behavior as well. Indeed, in the low energy part, we may have a bunch of very well distinct excitations, which are usually best described starting from a single or few particle Hall perspective. Otherwise, at higher energies, we have this continuum region, which is known also as the giant resonances region, starting from 10 to 12 maybe, according to the nuclei under investigation. And this can best be understood in terms of liquid drop picture, so vibrations and oscillation of the nuclear surface. And probably giant resonances are one of the clearest manifestation of collective motion in finite nuclei, together, of course, with rotations. Giant resonances are categorized according to their multiple nature, so monopole, dipole, and quadrupole here, but also according to their isospin content, so isoscalar and isobector. In my work up to now, I focused on this sector of the this sector of the table, so isoscalar giant monopole resonances, and to some extent also to the quadrupole. These resonances, in some cases, are also interested because they are related to compressional properties of nuclear matter, such as the monopole resonance in particular is linked to the K-infinity quantity, which enter the nuclear equation of state, and the isobector dipole giant resonance is is associated to the symmetry energy, and the nuclear peripheral states, of course, of interest for investigation of astrophysical interest, such as collapse supernova explosion or also neutron star mergers. But which methods have been used in the last years to address this physics? Of course, we have equation of motion and valid space extensions of some of the many body methods, which I was mentioning before, such as IMSRG and coupled cluster, but those are mostly suited for very weakly collective excitation, so more of particle Hall nature. Otherwise, for these very collective excitations, there is the Lorentz integral transform method for applied on a coupled cluster reference state. But these have been mostly realized up to date in spherical systems. Here an example for the isovector giant resonance in oxygen-16. And otherwise, more recently, also symmetry adapted version of the no-Koshel model has been employed to investigate, again, giant resonance in spherical nuclei, such as helium-4, oxygen-16, and calcium-40, and with also a deformed exception, which is neon-20. Otherwise, the most widely used method, which was already very widely used in more phenomenological theories, is the quasi-particle random phase approximation, mostly realized with several different variations on spherical systems, also starting from a self-considered green function method, and eventually even been extended in recent times in the form of a finite amplitude motion version for actually and triaxially deformed systems. But let me now talk about the method that I have used in my work, which is PGCM. As I was mentioning before, we are trying to solve the Schrödinger equation, and in open shell systems, we have strong static correlations which show up in the form of symmetry breaking reference states. That's why in the GCM, one usually starts from a set of constrained HFP solutions, which depend on some generator coordinate Q, which can be in principle any possible parameter, but must be chosen in a sense. So to encode the most physics possible for the physics case that we are trying to describe. For instance, since in giant monopole resonance, we know that the radius is going to play a most prominent role. I will be always constraining the solutions on the mean field radius, I mean the root mean square radius, sorry, and also to some extent to the formation. Then we mix these constrained HFP solutions into the PGCM ansatz with these linear coefficients F, which need to be determined, and this is achieved solving the variational Hill-Wheeler-Griffin equation, basically just minimizing the energy, of course, which eventually allows to rewrite the whole problem in the form of a Schrödinger-like equation, demanding the evaluation of these two objects, which are known as the Hamiltonian and norm kernels, such that you see that eventually we are just diagonalizing the original Hamiltonian, but in a much smaller physically informed Hilbert space. Of course, here I was mentioning the projected GCM, and there's no projector at all in my slide. This is just because I didn't want to burden excessively the formalism, but all the results that I'm going to show includes this projection procedure, which enables to provide solutions preserving restoring the quantum numbers, the good quantum numbers and the symmetries of the original Hamiltonian. In the next slide, I will be showing mostly this kind of plots. So which is the monopole response. In this case, that's the square operator is the one which is connecting the excited state to the ground state, and the transition probability between excited and ground state will be given clearly by the height of the peaks that I'm showing, whereas the position is represented by the energy of the excitation itself. In principle, even as I was saying before, that we are diagonalizing an Hamiltonian even if in a reduced space, the outcomes of the calculation always are discrete, which should be shown in the form of these discrete bars. But for just visualization's sake, I will be convoluting these bars with a 0.5 MeV Lorentzian smearing, but just for visualization's sake, there is no more profound physical content in this. Otherwise, another very interesting quantity for this kind of investigation, of course, are the moments associated to the distribution, which are nothing more than the mathematical moments of the strength. And these are related to the most relevant features of the spectrum, such as the centroid here and the variance of the distribution. A few details about my calculations. I have realized I've been using PGCM and QRPA in a consistent setting, and I did a systematic study in the case of titanium-46 for all the different parameters which enter the calculations, and split more precisely, for instance, parameters entering the harmonic oscillator basis, such as its width or its dimension, and then there was parameters entering also the interaction. So I compare different level of, different orders of chiral interactions coming from this first reference, even if the results that I will be showing are performed at M3LO, so next to leading order. This Hamiltonian has been pre-processed via so-called in-vacuum similarity or normalization group, and the three body forces are treated in an effective way at the two body level following the prescription from this last reference. So, yes, sure.
And then monopole oscillations should relate to the oscillations around the moon. So how should one, and if I were to scale my expectations, they would be low, but I think you would be presenting them being very good. So can you comment on that?
So yes, we have no input in the first place for the compressibility of nuclear matter differently, for instance, from skirm interactions. I will be showing in the end how, for instance, my results extrapolate to infinity for this extraction of K infinity. There are very preliminary results, but they are not doing so bad up to now, and they are reasonable in the terms of the range usually accepted for the value of K infinity. But yeah. So here, I'm not going in detail in this slide because it's very busy, but it's just for giving a flavor of all the possible source of uncertainties that I was able to find in my calculation. If you find more, I will be happy to include them. And I'm using three different colors in green, the one which I am, let's say, mastering, which are under control at least, and otherwise in yellow, the uncertainties that I've been just touching upon, and the red quantities which I was not able to verify, but I selected some, but for which I'm quite confident, even if some further investigation should be needed. So you can see not everything is green. So yeah, I think I'm still pretty far from determining the whole uncertainty budget of this calculation, but I'm trying very hard. So let me now show you some results. So addressing at first the effects of shape coexistence and deformation physics in giant resonances. Here I am showing results for silicon-28. This is the energy landscape at the HFB level as a function of two coordinates. So the radius, I was saying before, is the most relevant coordinate when addressing the monopole, but also there's this beta-2 quantity, which reflects the axial quadrupole deformation of the system, because it is known that quadrupole and monopole couples very strongly in giant resonance physics, and the positive part of the axis for beta-2 provides prolate solutions, so rugby-shaped nuclei. and instead for the more than 0 partial negative part of the axis are oblate shapes, so pancake-like systems. You see that there are two different minima in this case, one in the oblate and one in the prolate part, such that shape coexistence, so the coexistence of different nuclear shapes at the same time, will probably play a role in this case, and also naturally deformation, since both minima are deformed. The lowest minimum, so the one associated to the ground state in this case, is the oblate minimum, whereas the prolate one is associated to an isomer, so an excited state in principle. But I think that PGCM is the right tool to address the effects of shape coexistence in this respect. Why? Because, for instance, here I am showing the monopole response for silicon-28, which I obtain combining all the red dots that I'm showing here in my plot. So I'm combining a bunch of HFP solution in this oblate well region. And this is the monopole response corresponding to these PGCM calculations. And we see that there is a very well-defined peak at around 17 MeV with some fragmentation at higher and lower energy. However, I also perform calculations combining HFP states both in the oblate and prolate well, so these blue dots, and the blue spectrum is the outcoming results. The blue and the red spectra are not very different in a sense. Of course, they are not the same, but there are not really qualitative divergences, such as we may think that we understand that there is shape coexistent, but not mixing in this case between the two minima, since the two different configurations are not talking to each other, such that maybe it would be interesting to find nuclei in which these kind of effects would be more prominent. However, we can have a closer insight to understand why this kind of mixing is not happening. Indeed, here I'm showing the intrinsic PGCM collective wave function. This is not really a wave function in the mathematical sense of the term, but provides useful information about the probability distribution of the ansatz into the coordinate space. And you can see here the ground state wave function fully lies into the oblate well, whereas the wave function of the isomer is completely separated from the oblate one, and is instead in this oblate part of the landscape. One could also observe the wave function of the resonance state. In this case, we see that this is a radial vibration around the oblate ground state. In the end, if you compare this plot here with this wave function, the oblate minimum would be here, and we have a very clear radial vibration here with very little components from the beta-2 axis. Otherwise, one could also ask, what if instead we computed a wave function only in taking into account the prolate configurations? Well, this allows me to talk a bit more about the effects of deformation on the giant resonances physics. It is well known that spherical systems display two very well separated response for the monopole and for the quadrupole, meaning that you have peaks at two very different energies. However, in the formed case, the quadrupole splits on the different K component of the quadrupole, so the projection onto the z-axis, and the K equals 0 component also shows up in the monopole part of the spectrum, such that we have this very characteristic two peaks structure in the formed systems. And this is precisely what we observe here. Indeed, now I'll be showing the calculations combining both prolate and oblate configurations, but I will compute the response of the isomer, not on the ground state. And we see that we have precisely the same kind of physics that I was showing in the previous slide. So we have two peaks. The higher one at higher energies is a manifestation, let's say, of the spherical briefing mode in a sense, because this is a pure radial vibration around the former prolate minimum, whereas the first one is actually, which is mainly the coupling to the quadrupole, is actually a vibration both along the radial and the quadrupole coordinates, such that this is why we obtain this kind of coupling between the two modes. Before going on, I would like to show some comparison to experimental data. Here coming from different facilities. Must tell that the data themselves are not always in agreement between each other, because those kind of quantities are very difficult to extract, especially for light systems. But I think that we can reproduce quite well at least the shape of the data with this method, and also, I mean, getting very nicely the first peak, but also, I mean, the main peak, but also some minor structures. Also, I have to, I'm showing some less nice results for magnesium-24. In this case, the data are even more scattered, so are even less in agreement between each other. And the spectrum, the theoretical spectrum is very, very fragmented. As you see, there are many peaks. And I think that at least we managed to explain why the experimental data in the first place are so scattered, because probably it's very rich physics which is going on. Yes.
Do you have channels of transitions that have better data?
Yes, sure. I mean, in general, the fact is that there are very nice data, but for heavy systems, because in that case, there is very much collectivity in the nucleus going on, such that there usually one well-defined, I mean, for spherical system, and one very well-defined resonance with a broad continuum, or a couple of in case of deformed systems. But for light systems, the data are not so, I mean, are very difficult to extract from the experimental point of view. The overlap between Initio and experimental data is very poor in this case, because they are doing best where we are doing, I mean, pretty bad.
Question.
Yes.
You don't see shape coexistence in magnesium-24, right?
I see shape coexistence, but not mixing, probably, because in this case, again, would have a energy landscape with two different minima. The ground state one being the prolate one, but then this I must say that the calculations were performed in axial symmetry, so maybe breaking the axial symmetry and going to triaxial system, the landscape would become more uniform. And this is something I haven't tested yet, but could be the case. Okay, so this was just to say that, of course, better data will be very nice for helping to understand whether these many-body methods are actually doing well or not. And okay. Now, another interesting case that I would like to show you is about an interesting physical phenomenon, which is called multiphonon states. Here I'm showing a sketch for a very simple harmonic oscillator. First, the ground state would be the lowest state, and the giant resonances can actually be imagined as the first phonon in a harmonic oscillator picture. But of course, in this case, also higher lying state should exist. So resonances not built on the ground state, but built on other excited states. These are the so-called multiphonon or two-phonon or three-phonon states. And try to address those. I started from, let's say, a school case calculation, so which is not fully realistic. So a one-dimensional PGCM calculation, differently from before. Here I am just constraining the HFP states, it's a function of the radius, and then showing the energy, and you see that the energy surface is very smooth. And in this case, if we look at the monopole response, it seems that only one very sharp peak is observed, right around 18 MeV. However, if we plot the same quantity in a logarithmic scale, we also observe many high-lying states at energies which are close to integer multiple of this first giant resonance state. Then we can have a closer insight, one more, looking at the intrinsic collective PGCM wave function. In red, the wave function for the ground state, and in blue all the giant resonance states. So you see that this is one form of state, so would be the first excited state harmonic oscillator in the nice picture. But also the second phonon, so the second state as a wave function that fully, let's say, represent two phonon state. And eventually, another quantity of interest in this kind of investigation, which I'm showing here, is this busy plot. So in the X and Y axis, I'm again showing the monopole response in logarithmic scale, but then in the quadrant here, I'm showing all possible transitions between excited state. But as you see, only a bunch of them is actually showing up. It's not that I selected only these blue dots that I'm showing, but simply given that I'm plotting them, I mean, the dimension is proportional to the transition probability as well as the color. Only a bunch of them are actually visible, meaning that their transition are actually allowed only between neighboring states. So here, between the ground and the first phonon, first to second, second to third, and so far and so on. And if we plot the transition probability between neighboring phonons as a function of the phonon number, it looks very linear. So you can see this plot. And this is in full agreement, let's say, with a calculation I show here, which is for the harmonic oscillator. But this is a small case, one-dimensional calculation. What about more realistic PGCM calculation? So here I repeated the same exercise that I was doing before for silicon-28. So this two-dimensional energy surface, radius and deformation. And blue curve is my spectrum. And the dashed dotted blue line represent the computed centroid to be compared with the red dashed line, which is the experimental centroid, with the relative uncertainty in this dashed in this shaded red area. And we see that we are in pretty good agreement with the experiment. And in this case as well, if we try to evaluate transition to higher states, which are not visible in this response to the ground state, there is a two phonon state showing up roughly two times the energy of the first state, also with a transition probability which is close to 2 times the one of the first phonon. And we can again look at the intrinsic PGCM wave function, and we find more or less the same pattern in a sense. So this one radial vibration and double radial vibration for the second phonon. And eventually also showing the last plot. So here, all the possible transition between excited state, we observe that in the regions close to 2 and 3 times the energy of the main resonance, there are actually large transition matrix elements, such that we have, I think, good candidates for this kind of physics, even if from the experimental point of view is probably very, very elusive. And the last topic I would like to highlight is the connection to astrophysical quantities. Why is even worth trying? Well, the fact is that the nuclear compressibility is not something that we can measure in infinite nuclear matter, but for instance, something that we can measure is the giant monopole resonance centroid. The same for the symmetry energy. The symmetry energy is associated to the giant dipole resonance, but also to the dipole polarizability in little skin. And this is another quantity that I will address maybe in further studies. But coming back to the monopole, here I'm showing the compression modulus, the effective compression modulus in finite systems, which is defined in this way, with the average energy of the giant monopole resonance. And I will be comparing a different definition of the average energy, so naturally the centroid, but also other definition of average energies related to the moments of distribution. And observe that here I am plotting this Ka quantity, so the finite compressibility as a function of the A power minus 1/3. Such that we can extrapolate with a very simple linear fit to infinity going to 0 in this case. And in all cases, so I'm comparing both PGCM and QRPA results, also with different definitions of the centroid, of the energy of the resonance. And in all cases, we fall into this shady gray area, which is, of course, it depends to whom you ask, but in generally is the region which is commonly accepted for the compressibility of infinite nuclear matter. But I mean, these are just very, let's say, basic results, preliminary results, sorry, only computed a few nuclei, and definitely more systems should be computed before making quantitative statements in this respect. So come to the end. Starting mentioning all these frontiers, and I told you that I was addressing spectroscopy, potential systems, trying to quantify the uncertainties. I hope that I convinced you that PGCM can be considered a reliable tool for ab initio spectroscopy, with an asterisk next to the word ab initio, because of course there are many aspects that need to be addressed in a better way in order to really have a full understanding on the uncertainties at play. But also that we can access with this method the new observables and physics case that are been very scarcely investigated in ab initio nuclear theory before, which are the perspective. Well, first, as I was telling before, a deeper understanding of the uncertainty quantification, which maybe could also rely on some eigenvector continuation techniques, and also a systematic comparison, so more calculations for more diverse range of systems, and the comparison to new and existing experimental data. Then I didn't touch upon the subject, but I'm also interested in trying to restore symmetries in symmetry breaking QRPA. But eventually, so the project is to reach heavier systems, possibly combining PGCM with valence space IMSRG calculation, such a way to define sort of valence space PGCM for ab initio calculation, in order to be able to address heavier and heavier systems, which can actually better constrain also this extrapolation to infinite matter, which is of interest for astrophysics. So I would like to thank all the people I'm working with and you all for your attention. Thank you.
Thank you. That's very nice talk. So, questions?
Yeah, Andrea, very nice. So just like you're talking in Vancouver.
Yeah, more or less.
Yeah, and I mean, as good as you're talking.
Okay.
My question is about the multiphonon times
Yes.
46. So what is this? What is the signature that this picture is working in terms of comparing with experiment?
Yeah, the fact is that the problem, I started from Monopole because it's the easiest case for this kind of calculations. But multiphonon states were observed only in the giant dipole, in the dipole channel, in very heavy systems, such that this is maybe worth trying, but probably are quite far. But also in one exception in the quadruple channel for calcium-40, and this, however, really at reach for us in this moment. So it's definitely of interest to perform this kind of calculation. You have seen before how difficult it is already to characterize the physics of the giant resonance of the first phonon for light systems, and I think that for reaching this very exotic physics would be pretty difficult in the Monopole case.
Can I follow up on this question? But
Yes.
it wasn't clear whether you were advocating the mixing of one phonon with two phonons, or because this two phonons was a characteristic on a tail
Sorry?
of the Straits function. So were you talking about mixing of one phonon and two phonon states?
No, you're just saying that to my best knowledge, there are no microscopic calculations in the multiphonon sector.
So you still continue on the model level and argue that there may be some.
Yes, yes.
Okay.
But then also one point could be better understand how this higher quantum physics reflects onto the response to the ground state, if there is any signature, because this is what experimentally would typically observe. Yes.
That's a good question. I'm going to understand some of these plots between the multiple. So the blue one is the dipole, the dipole and monopole, is correct?
Yeah, sorry, I didn't explain it. I mean, because before was in over years now. So the blue one is the monopole response, just in linear scale. And then in red and green, I am multiplying it just by increasing numbers to show that there are also structures at higher energies, which otherwise in the linear, let's say the original state would not be visible. Such that, but you can see that these states are very, they present they better manifest not when coupling to the ground state, but when coupling, for instance, to the giant resonance itself.
So that means that probably you cannot propagate from the ground state. Currently you have less chance to see.
Yeah, it's very difficult because it's a two-step process. So you need to have an excited state in the first place, and then for instance, in standard physics is investigated using alpha scattering, and it means that the first excited on alpha and then another one in a very short time scale.
So could you discuss more about your as a PGCM and the RPA stuff?
Sorry?
Could you discuss more about your method, the workflows, or how do you get your free function, and then use PGCM to get the resonance?
Yes. So no, sure, there's no problem. So okay, even here. For the first part of the calculation is I perform a bunch of HFP calculations, so mean field linear calculations, constraining these HFP states on one or more coordinates. In this case, constraining the radius and the deformation at the same times, in order to be able to produce the original landscape of energy. But then, for practical limitations, we need to select only few of those states, because I want to just get too expensive, and combine them together. So this is what I show here. For instance, the red dots. We have all these set of HFP states, and they are superposed in the PGCM ansatz with this. In this way, the ansatz is just a linear superposition of the HFP states. Then one proceeds to evaluating all these kernels, so all the sandwich between different HFP states and the Hamiltonian, or with themselves in the case of the norm, and you arrive at this kind of Schrödinger-like equation, and this is very easily solvable, so diagonalizing the reduced Hamiltonian H. But instead of that, for diagonalizing the full Hamiltonian, which is I don't know how big, and you end up with a Hamiltonian which has the dimension of the number of states that you included in the ansatz. So if I included 100 red dots, then I will have a matrix whose size is 100 by 100, and diagonalizing this, we end up with these F coefficients, which are again vectors of the problem, and we can build up the PGCM wave function for the ground and for all the excited states.
So your starting point is carrying actually is evolution of SRT, right? After
Yes,
that,
the current fraction is 30 volt. Yes.
So have you checked the flow parameter of the SRT for your final result?
So in principle, of course, the results should not depend on the flow parameter. In our case, it is not fully true. But in what sense, how do you mean for
Because we have done some calculation, starting from current potential and do some RP calculation,
Yeah.
we found that the result, final result, the response function will highly depend on.
Yes, I mean, I have some. I think I have some backup slides here. I mean, in principle, of course, one should not observe this kind of dependence because it's not physical. But then, as a matter of fact, this is observed. Okay. Here, yes. Here are the two curves for two different parameters of the SRG flow. We have taken one which was observed to be, for which it was observed that the PGCM or the PGCM plus perturbation theory, which is supposed to be the, let's say, converged many-body method, didn't change at all. So we postulated that this 0.8 parameter is the right one because it doesn't introduce, I mean, it does introduce, I mean, it captures the correlation which are also captured by the particle perturbation theory on top. But definitely, I would like to perform more calculation with more parameters and find some form of convergence in this respect. Because otherwise, this is why it is yellow. It's not really under control.
Does that mean like if you change alpha, can you service or change?
I think yes. I mean yes, because eventually the positioning of the sensor, of the main peak reflects how steep is the surface. So it's changed. Okay. I mean, in my case, medium mass is titanium 46, but probably for someone it's quite light. I don't know.
Experimental parameters. Is there anything you kind of wait for from experimenters?
Yeah. Yeah. So more precise calculations for these monopole spectra in the light medium mass light to medium mass systems, let's say, because otherwise all the reliable information is just the centroid, but this doesn't tell very much. So I would like to have precise spectra as we can have for heavier systems, and also it would be interesting, I think, to use the theory itself as an input for the data analysis, because I know that in this kind of frame, the multiple response is very much model dependent, so strongly relies on some physical and theoretical input, and maybe yeah.
Any other questions? While people are thinking about that question, can I ask, can you go back to the uncertainty UQ budget? Do we have experiments here? Yeah. We still have a few minutes. You want to highlight something?
Yeah, sure. So in this case, the first parameter which I have addressed is the size of the harmonic oscillator basis. And in this case, so basically I repeated the calculation for increasing size of the basis as what I observed it as Emacs. So 10 major harmonic oscillator shells were already enough, in the sense that when going farther, for instance, at 12, the predictions didn't change at all. And typically the quantity which I use to address this problem is to give a number is a very rough estimate of the certainty in this case, but is the relative difference between the two last points of the converging series. So when I say that's a 0.6% error in this case, I mean that's sort of a relative difference of 0.6%, and similarly for the dispersion. What was difficult here is that also we are trying to put an uncertainty on something which is not just one number, but it's a whole spectrum. So this is the most naive way of doing this, but I think I would like to.
Correlation.
But then of course we have the harmonic oscillator with in this case as well the results are converged quite nicely, You see that the yellow and the yellow and red curves are pretty overlapped, and also the centroid is converging very nicely. I tested different truncations for the chiral expansions. In this case, of course, between 2LO and 3LO, even the spectra are not the same, but at least not too dissimilar. We see a trace of convergence concerning the centroid and the dispersion, but would be interesting also to have some higher truncations, such as and 4LO maybe one day, but by now we're not there yet for the three-body part of the Hamiltonian. Then otherwise, yeah, I mean, I'm not going to detail, but there are many body truncation because PGCM by itself is not converged from the many-body point of view, in a sense, because in terms of absolute values, for instance, we are quite far from the ground state energy. But what we observe is that the comparing PGCM or PGCM plus perturbation theory, relative quantities are more basically the same in the sense when this kind of collective physics is addressed. This has been checked up to now only for low-lying states, so rotational states, and should be verified also for this kind of.
What is the typical variation? KEV or
for the absolute or relative?
for relative?
Relative, you can. I think 1 or 2%. I think it's written. Yeah, no, it's not. Or the order of 1%, 2% for these low-lying states. In a sense, meaning that but that is a rotational kind of physics. So perturbation theory is not doing much about the rotations in that case. The PGCM is already capturing all the rotational physics. This may not be the case, for instance, for vibrations, and that's why it's in right sense need to be tested. I would like to compare with PGCM PT calculation, and then yeah, there's a bunch of dependence on the SRG parameter, the choice of the coordinate of the collective coordinates, which is not systematic, and the treatment of three-body operators, and also the influence of the variation of the parameters entering the Hamiltonian itself. Yeah, many things to keep track.
Very helpful. So you have a dominant one, SRG dependence give you 10%.
Yes.
Right. So do you have a feeling about the last one, Hamiltonian parameters?
No, that in that case, no, because I never tried. My poor man way of trying to address this problem was seeing different Hamiltonians, but they were not performing. They are really different Hamiltonians. They were not even at the same parallel order. So what I would like to do is, use an extreme Hamiltonian and trying to write the up to now is.
If we have a lot of people interested in animators.
Yeah.
Any questions? More questions? No. Okay, then we're gonna ask the last one.
Okay.
Yeah. It's about the tricky thing about the adding imaginary part when you calculate response function.
Yes.
Adding imaginary part. How do you decide the size of that? Because it's not in your error budget either.
No, in PGCM there's no imaginary parameter. Then I'm just adding the. Okay, you meaning that's mirroring. But okay, but that's is just for helping visualizing the strength. Yeah. But in my case, there's no. This is not in the budget in a sense because it's not something which there's no physics in
but
this.
if you change that parameter, you'll all those peaks.
Yes.
Will change the shapes, right? The shapes will change.
Yes, but all these uncertainties in a sense are evaluated starting from the discrete values so there's no continuum.
There's no true continuum.
Yeah, there's no true continuum.
Okay. I'm happy so. Okay, now let's speak again.